Now, right before the previous video was cut, okay, due to memory issues, we were already describing how these new yellow hydrogens, H sub Y, are all going vertically down. So again, just imagine that's yellow as well, okay? And so if we go here into our two-dimensional drawing, so again, 1, 2, 3, going this one here is this one going vertically down. There's a hydrogen sub Y for yellow. And here in the back as well, skipping a carbon, you'll go down and there's going to be an H sub Y somewhere down here as well. Okay, so we can just fix our drawing a little bit later on. Now, once you have all of these structure or hydrogens, red and yellow, going vertically up and going vertically down respectively, let's now get ready to prepare our green little atoms, no? And what I want you to do is that, okay, take these green atoms and put them on the remaining slots on where all of the vertical red hydrogens are. Okay, so where you have a vertical red hydrogen, I want you to put a green hydrogen there. Okay, where there are red ones. And you'll notice that unlike the red and the yellow, the green ones are all going sideways. They're all going sideways. Okay? So, if you position your drawing correctly, you'll notice that the green ones are going a little bit here, a little bit this way, and a little bit that way. So these are the H sub G, or the green hydrogens of our cyclohexane. Okay? So there. Okay. And then last, you'll have 3 of these blue lollipops, and you'll do the exact same thing that you did with the green ones. You'll insert them to the ones where, or rather to the final slots you have, and those final slots will be on where the yellow atoms are. So the remaining slot on where the yellow atoms are. Okay, so those carbons will have 1 slot left. Insert the blue hydrogens into that. And you'll notice that just like with the greens, all of the blue atoms are actually pointing not vertically up or vertically down, but sideways as well, either towards you or away from you. Okay, so there. And going to our drawing, we'll draw them going this way. H sub B for blue, H sub B for blue, and H sub B for blue. Okay. In your module, there is going to be a proper way to draw this chair conformation of cyclohexane. So I want you to go through that module and really study on how you draw this properly and how you draw all of these different hydrogens or different substituents pointing out either up or down or sideways from the ring. So all of these have very specific angles. Okay? Now, before we move on to drawing or creating structure C3 star, I want us to pay attention into the structure of this cyclohexane. All of the components going vertically up or vertically down, meaning the red hydrogens and the yellow hydrogens going vertically down, these are all called eggshell substituents. So eggshell. Yellows are also eggshell. Like in the globe, the axis is what's going up and down. And just like in the globe, on the middle of the globe, on the side of the globe, These are what we call the equatorial positions. So in this structure, the green hydrogens are on an equatorial position. Oops. The blue ones are also on an equatorial position. Now, there is a reason why I colored them red, blue, yellow, and green. Okay? The two eggshells are different. The two equatorials are also different from each other. The eggshell positions of these hydrogens going vertically up are known as the eggshell up positions. And the eggshells that are going vertically down are the eggshell down positions. Now here's where it's a little tricky. The equatorials are all more or less pointing sideways. Sir, how do we know if they're up or down? Well, if you pay very close attention, you'll notice that some of them are pointing sideways but slightly up. Some of them are pointing sideways but slightly down. But if that's not very clear to you, all you need to do is once you've identified all the eggshell positions of a particular carbon, let's say this one, okay, and this particular carbon here, okay, where I'll put a happy face, that carbon has a hydrogen or a component, yellow, going vertically down, an eggshell down. This blue hydrogen over here is in an equatorial position. It's going sideways, but it's higher than the eggshell down. So this will be an equatorial up position. So this blue hydrogen is in an equatorial up position. Now let's look at the carbons that have the green hydrogens on them. So perhaps this one here, where I drew that green dot. That carbon with the green dot has a hydrogen that's red going vertically up, so an eggshell up hydrogen. This tells us that this green hydrogen, which we already know is an equatorial hydrogen, is specifically what we call an equatorial down hydrogen. Okay. Being up or being down matters. It's part of the structure. It also tells us whether or not certain components are cis or trans to each other. Okay? So just like with your cyclopropane, cycloalkene, and your alkenes rather, you can also have cis and trans structures or stereoisomers in a six-membered ring structure. But rather than looking at just relative positions visually, we have to denote their up or down positions. Components that are both on an up or both on a down will be cis to each other, and two components that are one up and one down from each other on separate carbons, importantly, are going to be trans from one another. Now, there's another concept that we have to look at. That is, we have to look at which components are closest to each other. Going back to our model, okay, finding which two components are closest to each other will require for us not just to look at it sideways, but in all angles as well. Cyclohexane chair systems are very unique in that it will have components in the eggshell positions, either eggshell up or eggshell down, interact with each other the most. Okay? And these interactions are called 1,3 di-eggshell interactions. Okay, 1,3 di-eggshell. So 1,3. Let's remember when we drew or when we added all our hydrogens. Remember, we skipped one carbon. We counted 1, 2, and then skip that 2 and go to a 3. So let's pretend this carbon here is our carbon 1. It has that eggshell up red hydrogen. We'll count 2 and then 3. So this is in position 1. This is in a position 3. The same thing will happen if I drew or go the other way. This is 1. This could be 2. Relative position number 2. This would be 3. Okay. Any components that are both on an eggshell up or both on an eggshell down would be very close to each other. So these red components and these yellow components are close to their fellow components. So like these 3 reds are the atoms that are nearest each other on this structure. And these 3 yellows, well, I'll pretend yellow here, are also the atoms nearest each other in this structure. Okay? Because they are near, they can interact with one another. So the interaction, the repulsion that these 2 atoms have, or these 2 atoms and these 2 atoms have, are called 1,3 diaxial interactions. And the same thing will happen here. These 3 yellows will also have 1,3 diaxial interactions with each other. So what does that tell us? Okay. Well, sorry, let's just compare it first with the equatorial. If you look at it in the top view, okay, you'll notice that all of the blue and greens, regardless of being equatorial up or down, are all radiating outwards from the ring. That tells us that these components are all spaced out far away from each other and avoiding as much repulsion from each other as possible. Okay, now what does it tell us, Sohain? Let's go back to what I was trying to say about having components that are big and bulky, like large atoms or large chains or large branches. If we have to put a large branch, let's say like this random alkene branch, on our cyclohexane molecule, it's actually quite preferable that they are not on an eggshell position. Again, let's go back to eggshell interaction. So look at this. I have a 2-carbon alkene chain. And look, if it's on an eggshell position, what's happening here? There are collisions. It is trying to take up the same space as these 2 other red eggshell positions. Okay, so let's put it back. Let's repair our molecule again. Now, let's try to replace one of the equatorial positions. So I'll take the equatorial green hydrogen and replace it with that weird chain, with that side chain, that large bulky alkene group. And notice, if I rotate it, it's not really colliding with anything. So having large groups is not very favorable for the eggshell positions, but it is quite favorable for putting them on an equatorial position. So if you're analyzing cyclohexane structures, having the larger groups and more of them on an equatorial makes that structure more stable, and having more groups that are large on an eggshell up or eggshell down position makes that cyclohexane unstable. Okay. Now, so far we've only really just looked at C3, but what about C3 star? That will be the subject for our next video.